Okay. Ladies and gentlemen, all the technological things are finished and we are ready to start. So it's a great, great pleasure and a great honor for us to have Stephane Mallat visiting. Stephane is here for a very, very happy occasion. He just got an honorary doctorate from the Technion. And honorary doctorates in the Mallat family go by heritage. So his father was an honorary doctorate from the Technion, and his grandfather was active in securing the permit from the Ottoman Empire to build the Technion. So
we are all here.
So Stephane Mallat has a very, very strong connection to the Technion, but I'll tell you, rather than telling you about him, which I'll do briefly before I let him finally start to speak, I'll tell you the following story. I was a young professor at the Technion when Stephane's father comes to my office. I didn't know his name, I didn't know him at all, and he drops by my office and says, I understand that you are doing things with image processing, signal processing. My son is doing that. So I say, who is your son? He says, oh, Stephane Mallat. I said, Stephane Mallat, the guy with the wavelets, papers, everything I knew about him, of course. And I said, yes, but I didn't know that there is connection to the Technion. And says, yes, yes, his name is Mallat, in fact. It comes from Mallat. Mallat is a French version of it. And ever since then, and he said, if you want to get in touch with him, here are his coordinates and so forth, and we are ever since in touch. So it's a great, great pleasure to have Stephane. Stephane is, of course, his contributions are well known. Wavelets, lots of other developments after wavelets. Stephane is a member of the French Academy, and he is a member of the US Academy of Engineering. He has many honors, and he is now from the Collège de France and from the École Normale Supérieure. Prior to that, he was at the École Polytechnique, which is also a rather important French school, which produces all the important politicians, which I'm not sure they are very proud of.
Not all, but that's what.
So, but in any case, it's always a great pleasure to have Stephane around, and he's going to tell us about his latest work, in which he tries to sort of make sense of the new data craze.
Yes.
Okay, so here.
Thank you very much. Thank you. Thank you very much, Freddy, for this so warm introduction. So, yeah, that was indeed a very emotional evenings and so on because of these family connections and all the family who came to here. So I'm very happy to be back in normal life now. And in fact, probably the person who has been working the most and for the longest time in this topic is Alan Pinkert, who is here on the neural networks. So to speak about, in some sense, the mystery, the mathematical mysteries around these neural networks. And I'll do it from an application light, which is not just image processing, but also physics. In some sense, physics, the advantage of it is that we do have information about the underlying functional, there are equations. So it defines a setting which is a bit simpler to try to define the mathematical problems. So from the mathematical standpoint, the question which is underlying all this is the fact that we are trying to approximate functions of an x, which is a very high-dimensional x, where x is the data. So, for example, x would be an image with about 1 million variables corresponding to the pixel, and f of x would be the class of the image. Now, if you look at the same problem in physics, x would be the state of the system. So, for example, if you have a molecule, it would be the position of each of the atoms, the number of charge, and f of x would be the energy of the molecule. And the whole question is, can you regress such a function from a limited number of examples, despite the fact that you are in very high dimension? The other type of typical applications is to build stochastic model. So in that case, f of x would be a probability density if it exists. And obviously in physics, one of the outstanding problems is to understand turbulence. Can we build models of turbulent fluid in 2D or 3D? And here again, x is the state of the system. This is the vorticity. It would be the value of the vorticity at each point. And now people are doing even more crazy things. They try to define the probability distribution associates to phases. Can we define a random process whose realization would be phases, which would mean you could build new realizations which are phases? And that looks like a crazy question. The only thing is that nowadays people do that kind of thing, so we need to try to understand a bit what's behind. So briefly, from a math standpoint, why is this problem so difficult? It's obviously because of the curse of dimensionality. If you look at it from a bit of a nice point of view, you think, okay, I have xi, I have f of xi. The only thing I need to do is to interpolate. So to know the value of the function f at the point x, one reasonable strategy is to look at the value of f in the neighborhood and then do a local interpolation. Now, why this never works in high dimension? It never works because you almost never have a close example. All the points are very far away one from the other, and to realize that, you can just take the cube, 0, 1 in dimension d. If you want to make sure that your x is at a distance at most epsilon from an example, you need to sample the cube, and in dimension d, you'll need epsilon to the minus d points. If you take for epsilon 1 over 10, which is not so small, d 100, 10 to the power 100, it's already more than the number of atoms in the universe. Now, the problem is that we're not going to be in dimension 100, but rather 1 million. So it's a totally hopeless problem to try to approximate a generic function f of x from local interpolation. So the fact that we can do it on many examples means that the function f of x that we try to approximate have some very, very strong regularity property, such that a relatively limited number of examples is sufficient to build these interpolations. And x doesn't really belong to the whole space Rd. It belongs to a subpart of the space, which can still be of high dimension. So the problem is a couple problem. Understand the nature of the support of the data, which is not a low-dimensional manifold. If it was, then the problem would be easy. It's not. And understand the property of the f. And hopefully build functional spaces around these things. And we are not at that stage. So why is this problem there? The problem, as you know, is there because right now you have remarkable algorithms which are, and in particular, as Freddie would say, this is the craze of deep networks. But the fact is this craze is more than a craze. These things work quite well, generalized. There is a huge industry behind. So briefly, I suppose all of you know these algorithms. In the case of an image classification problem, the input x here is the image, about 1 million variables, and you cascade a linear convolutional operator and a nonlinearity. So the nonlinearity is called a relu, which is just taking the maximum of the number and 0. Very simple nonlinearity. And then you cascade. So the next stage, the second layer coefficients, each image here is built by doing a convolution with a small filter, typically 3 by 3, 5 by 5. On each of these images, you sum the result and apply the nonlinearity. You cascade until the last layer. You do a linear regression, a linear combination, and you get your approximation. Now, as you know, the parameters of this network are basically the coefficients of the filter. You will have several millions or hundreds of millions, which are adjusted by stochastic gradient descent in order to minimize the error obtained here over the example. Good. What is surprising is that it generalizes. These systems have exceptional results, not just for images, sounds, languages, image generation, regression of phenomena in physics. That shows that somewhere there is a mathematical mystery. It's not anymore about images, about sounds, about physics. That means that somewhere there is a mathematical structure which is common with all these fields, which explains some sort of regularity, which can be approximated by this kind of structure. So the question is, why? What is the nature of this regularity? And can we build a theory of all that? From an application point of view, what people would like is at least to have something which is interpretable. Right now, this is a black box. People have no idea why it works, when it's going to work, when it's not going to work. So being able to understand what this black box is doing is very important also for applications. So what I'm going to try to do is not obviously give the solution, but I would like to show you that there are sources of regularities that plays a very fundamental role in this problem. The first source of regularity will be the multiscale organization of the problem. Very classic idea of hierarchy. There is also the fact that there is a lot of information about the symmetries of the problem, and these systems are building invariance and therefore reducing dimensionality. And sparsity will come in, and that's where Mickey Lab will come in with it. So that's the three elements that are going to come in. And there are a lot of strategies to attack that kind of problem. In fact, right now, each one who has a hammer in hand is trying to use his hammer to bang on the problem. I'm going to do the same. I'm not going to look at the optimization problem. I'm really going to look at it from an approximation problem. In other words, try to understand, can I take such a structure, simplify it, and get the same kind of numerical results, and why? Okay, the first argument is multiscale. So you can view it in general. When you have a system with the interacting body, it can be particle, it can be pixels, agents in social networks. A priori, any particle will interact with any particle. You can reduce the number of interacting terms with a very classical strategy which is used in physics, in particular with multipole, which consists in looking at these interactions hierarchically. The very strong interactions are with the closest particle, your neighbors, the closest pixel or particle in the physical systems. Now, more far away particle, you can look at the interaction on this one by looking at an equivalent field over this particle, which would correspond in a network, let's say, a group of friends, companies, or even more far away particle like countries. I mean, you may think that you don't need to know who are the different people in Russia, which is true, but you can't neglect them, because if you neglect them, you neglect Russia, and who knows, if there is a tension between Russia and Israel, it could have an impact on your life. So we cannot neglect anybody, but you can summarize their interactions through a group. Why is the problem very difficult? The problem is very difficult because the groups have interactions. And the whole problem is to understand, yes, you've reduced the interaction with log D groups, but what is the nature of these interactions between these groups? And that's a very classic problem. So to separate the scale, this is not difficult to do. Well, let's quickly look at the wavelet transform. What is really the open problem since the 1970s is to understand the interactions between the group, the interactions between the scale. And what I want to show here is that, bizarrely, neural networks have something to say about how to build these interactions. So the talk, basically, I'm going to begin with scale separation and explain the problem. And then I will show that, in fact, how you can build these interactions, which are crucial to reduce the dimensionality of the problem. Phase plays a major role, and the nonlinearity of the networks applies on it. And it took a long time. You know, phase is something usually you eliminate when you do harmonic analysis. It's a pain. The phase of the Fourier transform, you want to remove it. you change your basis, you compute like a wavelet transform, and you take the modulus. What I want to show is that here phase is very fundamental. So first we'll look at linear models across scale, and I'll show that it's enough to build models of things such as turbulence, and we'll look at applications to quantum chemistry. And then we'll go to nonlinear models, and I will show here why sparse dictionaries plays a very important role. And that will be needed to really go to difficult classification problems such as ImageNet, or to generate random processes such as faces or things like that. So that's a bit the program of what I'd like to speak about. Okay, so the first thing is to separate scales. So I suppose most of you have heard about wavelets. This is now a standard math tools to separate phenomena across scales. The basic idea is that instead of taking a sine wave, you localize your sine wave with, let's say, a Gaussian, so you have the cosine and the sine part. And because it's localized, now you need to look at it at different scales. So we are going to scale the wavelet by a factor 2. So the support is going to shrink if the scale gets to 0. And like a sine wave, we're going to look at different orientations. So that's the rotation parameter. These are the rotated sine wave. Now, what we do in signal processing terms, it would be called a filter bank. We take the input image, and we make a convolution with each of the wavelets. So a convolution in the Fourier domain is just a product. So it's really a projection of the Fourier transform of your signal, your image, over each of the support of the wavelets. Now, a wavelet has a support located in a localized channel like that. It's a Gaussian translated in this region of the plane. If you rotate the wavelet, you're going to rotate the Fourier support. You're going to get an annulus like that. If you dilate the wavelet, you're going to dilate the Fourier support, and you are going to cover the whole Fourier plane, which explains why you have basically a complete representation. You can recover the Fourier transform from its projection in each of these frequency channels. So what's the problem? So that has been very much studied. I'm not going to speak about orthogonal basis or complicated things like that here. The problem is, once you've projected in these different channels, they are totally decorrelated. What I mean by that is that if you look at the wavelet coefficient in one channel and in another channel, if you sum, you compute the correlation, it's always going to be 0. Why? Because if you compute the Fourier transform, the Parseval formula, you have the product of the Fourier support of the wavelet, which are disjoint, and that gives you 0. Sorry?
There is a prime.
There is a prime? Oh, yeah, there is a prime here. Wow, following one. 1%, that was a test, of course. So,
I had coffee.
Yeah, you had coffee. So let me show you on an example. This is an image. These are the wavelet coefficient, cosine, sine at the finest scale. And then you build a filter bank, you get the average image that you split again in the highest frequency, low frequencies, and so on. Now observe. Across scale, you basically see the same kind of structure. So they are very dependent. If you view that as a realization of random process, the different multiscale are very dependent. But if you compute the linear correlation, it's 0. So the whole problem is to capture the dependence across scale. How does the scale relate one relatively to the other? Let's try to see what we are usually doing in statistical physics. So the problem is the following. You want to build a model of, let's say, a turbulent fluid, or that's bubbles organization. What we know is that it's a stationary process. So the probability distribution is invariant to translation. That's the nature of the symmetry of the problem that we know. So how to build a model? The standard approach is to say, I'm going to constrain this model by computing moments. So expected value of some nonlinear function phi m, compute the moment, and then define the probability distribution as the distribution which has a maximum entropy conditioned to these moments. and you have a convex optimization problem, and you get a Gibbs distribution, which tells you that the probability distribution, if the optimal is reached, is going to be an exponential of a linear combination of these moment functions. Okay, standard moment functions which are used, second order moments. So if you use as phi m correlations for different points of your field, this is going to be a quadratic function. So this is going to be a Gaussian distribution. And that corresponds to the Kolmogorov model in the case of turbulence, Gaussian model having the same moment. And that's a typical realization. And that's a typical realization having exactly the same second order moment. And as you can see, you completely destroy all the geometry of the problem. Why? Because the different frequencies are now completely uncorrelated and therefore Gaussian independent. And so you cannot reproduce the alignment of structures which gives yield to the geometry of the phenomena. So the whole question in probability theory is how to build model of non-Gaussian fields. And obviously that's a very standard question. And what people did for essentially until now, compute high order moments. Okay, second order moments are not enough. Have a theorem which tells you if you have enough high order moments, you'll be able to approximate your random process, but it doesn't work. Why it doesn't work? Because the number of high order moments explodes. And the second reason is that high order moments are very unstable to outliers, and therefore you have a huge variance. So basically, it doesn't work to build models of any of these type of random process. People have been doing experiments with deep net, and they've been able to generate things that looked very good. The question is why? How come? Okay, let's look at a linear rectifier. What does it do? If you take a wavelet, I'm going to take a wavelet, and I'm going to choose a wavelet with different phase. That's the phase alpha. What is a wavelet transform doing? It's a convolution of your data x with your wavelet. And the real part, I'm going to put it outside, and then you apply the nonlinearity. That will be the only calculation lines I'm going to do in the talk. Now, your wavelet coefficient, I can separate the modulus and the phase. And what I want to show is that essentially a linear rectifier is filtering the phase. Why is it filtering the phase? Because it's a homogeneous operator. If you multiply A by alpha, which is positive, the alpha you can put it outside because it's the max of A and 0. So the modulus, which is here, I can put it outside. And what I get is the nonlinearity applied to something which only depends on the phase. And now I'm going to do a simple thing. I'm going to compute the Fourier transform relatively to the alpha parameter here. And I'm going to get the Fourier transform of this relatively to the parameter alpha. So now alpha is between 0 to pi, so that's an integer k. And what do I get? This doesn't depend upon alpha, it goes here. Fourier transform is just the shift by alpha. I'm going to get the phase multiplied by k. What does that mean? That means that when you apply this nonlinearity, it's equivalent to compute high order moments just of the phase, harmonics of the phase, but I don't touch the modulus. And that's very important because that's what will bring you stability. But the phase, I'm going to get all the high order harmonics. And from that, I'm going to show you that you can build all the coherence across scale. Why? Let's look at the wavelet coefficients. So it's a modulus, and you have this phase which is multiplied by this k factor, which is the harmonic factor. What is it doing? What it's doing is basically it's accelerating the frequency, which is going to be multiplied by k. So the problem is, if I have an information in two frequency channels, they are not correlated. They don't speak. How can I make them speak? I want this to overlap this. How can I do it? I accelerate the phase. It's going to increase the frequency, k equals 2, k equals 3, and now these things are correlated. So you basically apply your nonlinearity, which basically computes harmonics, and then, boom, you can just compute a stupid correlation, and it's going to build you your correlation. So let's do that. That's the wavelet with the phase. That's the linear rectifier. In the Fourier domain, if I can view it as computing harmonics of the phase. On an image, this is the modulus of the wavelet coefficients, the phase. The phase is accelerated. Now they move at the same speed. In the Fourier domain, that's the two Fourier transform support. After accelerating the phase, the Fourier transform moves from here to here, and now they are correlated. So I'm going to show you the kind of stochastic models you build from that. These are the original realization. I'm going to still compute linear correlations, but not of the wavelet coefficients, of the wavelet coefficients and their harmonics to the phase due to this nonlinearity. And then I define the maximum entropy process, and I just sample the random process. And here are the realization. And I just get log d squared moments, not d squared. And you can see now that the realization looks very much like the original in the sense of having the same kind of geometry, because now the phases are aligned across scale. You've built your coherence across scale with a covariance measure, but on a nonlinearity measure. Same thing for here and for here. And the number of moments is very much reduced, even compared to a simple covariance. And you get the kind of results that you obtain visually with DeepNet with much fewer coefficients, because now you understand a bit what's happening. Now, there are plenty of questions, of course, once you have that. How much physics is really captured with that kind of mathematical model? And also, can you go from models like that, which are really ergodic processes in the sense that this is homogeneous, to non-ergodic processes such as faces, things like that, that we're going to look at? OK, so that's the questions I want to address now. Now, before doing that, I want to go to applications such as classifications, which are about approximating functions, to see other type of problems are going to come into. So to build a classifier, typically classifiers of objects, the objects doesn't change when you translate it. So you also have a representation that you want to be invariant to translation. To do that, I'm going to use the same kind of strategy. I build my multiscale representation, and then I average in space. So that's the averaging kernel. It can be a Gaussian, or I can average over the whole domain. So I have a set of descriptors, but because I'm averaging the coefficients, I'm losing the high-frequency coefficients, which I recover by a second set of wavelet coefficients. I don't want to go in the details of all that, but the result is a representation where I have coefficients at different scale and interactions between the different scales. These are the interaction coefficients between the different scales. They are average in space, so these are invariant coefficients to translation. You can prove that these coefficients give you a representation which is also stable to the action of diffeomorphism. If your image is deformed, these coefficients, which are invariant to translation, or nearly, are just going to move by an amount which is proportional to the size of the deformation, which is important for classification. OK, so what kind of applications? First kind of applications you can get out of that are estimated energy of molecules. So in this problem, the x corresponds to an information about the position and the charges of the molecule. F of x is the energy. So the energy, if you translate the molecule, it's not going to change. And if you rotate the molecule, it's not going to change. So you have information about the symmetries, which are translation rotations. Now, quantum physics, the way these energy are computed is by estimating the electronic density. In other words, the probability of presence of an electron at any given point in space. To do that, you need to solve the Schrödinger equation, the n-body Schrödinger equation, which is extremely complicated, requires a lot of calculations. What we're going to do is something that will look naive. We are going to take this density, which we don't know how to compute. The only thing that we know is the position of the atoms and their charge. So we are going to represent it with a very naive density, which just represents the information about the molecule, where is each atom, and how much charge. So it's a sum of Dirac. Now, how are we representing the geometry of this molecule? With these wavelet coefficients. So how to interpret it? X is a bunch of Diracs whose amplitude depends on the charge. You make a convolution of a Dirac with a wavelet, you get a wavelet. So now you're going to get a sum of wavelets. It's as if each Dirac was emitting a wave. These waves are going to be summed up, and you have a nonlinearity. So you are going to have an interaction, an interference between the waves. And these are the output of this nonlinearity. So basically, you are capturing the geometry from the interferences of all these waves. You compute that at different order, and you do that in 3D. Then you compute an averaging, as I said, and a linear regression. So that's the network. You capture the geometry which linearize your different group action and symmetries. You build invariant, and then you try to estimate energy as a linear combinations of the invariant. In that kind of problem, surprisingly it works, in the sense that over large databases of molecules, these are organic molecules, you get basically state-of-the-art approximation of the energies. And to give you an order of magnitude, the errors here are 0.5 kilocalorie per mole. If you do numerical calculations with a DFT, which is the standard method based on Schrödinger equations, you get an error of the order of 1 or 2 kilocalorie per mole. So you get very close approximation, but they are trained on database which were calculated from DFT. You get about the same thing than DeepNet, but only on small molecules. All this has been trained on database of small molecules with 20, 30 atoms. Nobody has any idea whether it's going to work on very large molecules. And there are strong indications why probably it will not, or it's much more complicated. And let me explain why. Let's look at the same chain to see what is not working on image processing. So the idea is you use X, you build a fixed representation, no learning, just separate scale and compute interaction between scales. You compute your invariance, and then you just learn the final linear. If you do that on a problem such as digit recognition, which is just about analyzing deformation translations, that's going to work. Basically, whether you use a deep net where you learn everything or something like that where you don't learn anything, but you know in advance the nature of the symmetries and you put them in the network, you get the same result. If you do that on texture recognition, same thing, about same result. If you do that on a real difficult problem, ImageNet. ImageNet is a database with 1 million images, 1,000 classes, and the image looks like that. Here you have to recognize that you have a Dalmatian, but you also have cherries, that you have mushrooms and so on. It fails completely, in the sense that with a deep net, the first result in 2012, AlexNet had 20% error, and now it goes to 5%, even better than Visual System. And these systems don't go below 60% error. So somewhere, obviously, you need to learn. And the whole question is what is learned in this system. Now, if you would ask that question to Miki Elad, who is not here, he will tell you sparsity. You learn dictionary learning and so on. I didn't believe it, but I want to show that he may not be so wrong after all. So that's what's going to be the point of the second part. I would never say that if he was there, because otherwise he would use it for the next 20 years. But yeah, that's the point. Sparsity is going to play an important role. Okay, so dictionary learning, I imagine you must have seen that 1,000 times with his presentation or student presentation, but let me still do it. What's the idea of a sparse representation? X is going to be approximated from a vector z, which has very few non-zero coefficients. You are going to approximate x from z as x equal to dz, and d is the dictionary, which you can interpret as a family of patterns, and x is therefore viewed as a linear combination of few vectors stored in z, which is much more redundant than a single basis. How do you solve that kind of problem as a variational problem? You try to approximate, here x, here is x bar as d multiplied by z, and you impose that z is sparse, and the optimal code is the one which minimizes this for a fixed dictionary. Okay. So how do you minimize that convex cost? There has been for the last 15 years a lot of work. And there is one particular class of algorithm which are called homotopy algorithm, in which I'm going to speak in 1 minute because it's a very nice idea that we're going to here use that dates back to, again, about 15 years ago. Lars algorithm is an example. The idea is instead of solving the initial variational problem, you let the coefficient alpha go from a very large value to the final value you want. So you are going to make a continuation on the parameter, because when alpha is very large, solving that is a trivial problem or very simple problem. You are progressively going to reduce alpha. And there are algorithms which does that, in particular a soft thresholding algorithms that I'm not going to go into the details for the one who don't know. For the one who know, it's basically like iterated thresholding, an algorithms which is going to make a thresholding over an iteration, but the threshold is going to be progressively reduced, which corresponds to this continuation on the alpha here. The point is, nowadays, when you have an algorithm, you translate it as a neural network, otherwise nobody understands you. So that's what it means, the algorithm. You put x in input, and you have a matrix D. That's your nonlinearity. The nonlinearity is a soft threshold. That's the kind of thing that Mickey is doing. The only thing is that he's not using homotopy algorithm, but you can view it almost as a detail. And then you iterate on these matrices a certain number of times, and you get your output. Okay? You can view it as a network. Okay, so let's go back to the problem. The first algorithm was the one I described you. You put it in X. You know that you want to do scale separation with interaction of phase with your nonlinearity. You build your invariant, blah, blah, blah. 60% of error, very bad result. Then, and then I'm lucky Miki is not here, you do like Miki. So you begin with X, and then you apply your sparse coding algorithm. He doesn't do that. He iterates over it, so he gets better results. But if you were just to do it once, sparse coding, linear regression, 50% error. It's better, but not much better. If you go on these worlds, you first apply your invariant, and then you build a sparse representation. The error drops by a big factor. What does it mean? What are you doing here? You are building here with your dictionary a model of the interactions across scales, which is not anymore a linear model. It's a nonlinear model which is captured by your dictionary. And the reason why it doesn't work when you apply directly on the data is because the data has much too much variability. When you translate, deform, and so on, the data changes. So the dictionary would need to be absolutely huge. You first need to contract, build invariant before putting your dictionary. And there you get, so that was the latest results. AlexNet is still at 20%. At one point, it will probably reach. So the point is, what are we doing? We are taking the function, we are building this multiscale interaction with the interaction terms, and then we are putting a nonlinear model as opposed to a linear model based on covariance. What I want to show to finish is that if you do the same thing now to model a random process, you can get models of faces, bedrooms, things like that. And you can begin to understand what people are doing with autoencoders. Okay, so that's another crazy and very nice idea coming from these deep nets. What are people have been doing? They want to model faces. So what do? They take a face, they build a first neural network which transforms this face in something that looks like white noise. Then they take their white noise, and from the white noise, they try to reconstruct something, or the thing that looks like white noise, something which is very close to the original face. So they try to invert it. And then they begin with any white noise, and they reconstruct something that looks like a face. And what is remarkable, if you train that, for example, on bedroom, if one white noise realization reconstructs a bedroom, another white noise reconstructs another bedroom. If you do a linear interpolation here, you get different noises. If you reconstruct from them, you always get a bedroom. So that point is just the average of these two noises, and it gets you not the linear combination, but a new bedroom. That's as if all the bedrooms which you can view as a kind of completely crazy a cloud in your original space had been transformed into a completely flat manifold, so that the average of two bedrooms is now a bedroom. That's the same thing on faces. So the average of two faces, you see them as a video. They are always a face which merge progressively one into the other. So what I want to show is that one can understand that kind of thing with essentially the same kind of principle. So the first problem is the following, and that's the work of Thomas Angles. You begin from X, and you want to transform them in something that looks like Gaussian white noise. Now in math, the only tool that we have in high dimension to build a Gaussian process from something which is not Gaussian is central limit theorem. Essentially, it's the only one which operates in high dimension. So what are we going to do? Again, I'm monomaniac, so I'm going to build a multiscale representation, separate all the different scales, and then I'm going to do a linear mixture of that. This nonlinear representation, I'm going to average it spatially, and I'm going to whiten it, so then you get something which hopefully is linear, nearly Gaussian, but not white, and then you whiten it by adjusting all the variance, and you get something that is much lower dimensional, which hopefully is nearly white noise. That's the chain that we're going to use. So again, first you build your multiscale representation, then you reduce the dimension by averaging, and you get a vector of nearly Gaussian white variables. Now, from this, you want to go back to your bedroom. So you have an inverse problem, okay? You have done the transformation, and from this W, go back to X. What is difficult in this problem? U, which is this operator, is perfectly invertible. A wavelet transform is invertible. I use different phase, so the linear rectifier, if you take max of A0 plus max of minus A0, it's equal to A. So not only it's invertible, but it has an inverse which is linear, despite the fact that it's nonlinear. So U minus 1 is no problem. What is a problem? The mixing operator. When you apply your central limit theorem, you reduce dimension. This is not going to be invertible. But now you have a very standard linear inverse problem. you need to invert this operator L. What do? Sparsity. You have a non-invertible problem, but you have some prior information about X. If you know that X has some sparse representation in some dictionary D, and you can, in that case, what you invert is LUX, so it's going to be UX that you are going to represent in your dictionary. You can use that as a prior information to regularize your inverse problem. Again, you are building a model of your data across scale, which is a nonlinear model, which is captured by this dictionary. So that's what we're going to do. L is not invertible. We're going to use the fact as a prior that UX has a sparse representation in some dictionary D. And now what we know is W. But W is the linear operator L applied to UX. So we know that W, because UX is DZ, is now sparse in a dictionary, but which is LD. So Z is the code of W in this dictionary. This is the completely standard inverse problem approach when you have sparsity information. So how do you invert the problem? You begin with W. You build a sparse code of W in a dictionary LD. You get your code Z. What you are interested is UX, so then you apply D, and then you invert U minus 1. Now, you don't know the dictionary D. So how are you going to learn the dictionary D? By optimizing this single matrix in this whole network, which is going to reproduce the best reconstruction. In other words, you minimize the reconstruction error. This is essentially the same kind of algorithms that everybody do with autoencoder. The only thing is that now we just have one matrix in this autoencoder, which is this dictionary, which is building the model. And if you do that, that's what Thomas Angles did. So that's the original images. These are from the training set. These are the reconstructed images. That's a different data set than the reconstructed one. And then you can put random noise. And on the first database, that's the typical realization from random noise. Not perfect quality, but you can see that you begin, and that was a very small network, I should say. You begin to get realization random process, which looks like faces. And why do you get it? Because these faces are sparse in a dictionary, which is representing the multiscale interaction of all these structures. This is the same thing, but trained on the dictionary of bedrooms. So you can see that you get something which at least don't look like face, which somewhat looks far from bedroom. And you need to increase the size of the dictionary to get higher. You need, if you want to get details, again, the dictionary is basically the memory of your system. You need a bigger dictionary, a bigger network. Linear interpolations, that's what you get. If now you begin from a noise which reconstructs this image and another one which reconstructs this one, these are all the intermediate ones. And you can see that you reproduce all the linear interpolation property. This is thanks to the fact that at one point there was a theorem saying in that space of scattering coefficients, information linearized, which you get here through the reconstructed images. There is one problem which I think, one of the big problems in physics, in particular meteorology, very large scale computations, is to be able to do fast computations at very coarse scale on a nonlinear PD. To do that, you take, so let's say this is a turbulent flow. This is the low frequency turbulent flow, and you want to have your equation applied to that. But it's not going to work because you have an interaction between the coarse scale and the fine scale. So you need to have a model for the fine scale. In this case, the model for the fine scale is represented by this noise. And when you put the noise together with this low frequency, you can see that you reproduce typical realization of the original object but with different high-frequency properties, which in this case corresponds to different phase expression. So one of the questions now is to see whether one can use that kind of representation to have coarse grid, very fast algorithms, which works on the coarse resolution, but which captures the interaction between the high frequency and the coarse frequency. Different topic. Okay, let me conclude. So, what about deep convolution in general? I think it's very hard to get a global theory of deep neural network. I begin to have impression that these deep network almost looks like Turing machine. To have a theory of what a Turing machine can do, you can have a computational classes, but it's not going, the flexibility is absolutely huge. And when you look just at these nonlinearities, you see that the nonlinearities, the way we've been using them, when we applied them to wavelet filters, they were behaving as a frequency transposition tool which were creating phase harmonics. When you apply it in the context of dictionary learning, it was doing essentially soft thresholding. So the same object is behaving in a very different way at different stage, at least of these networks, which makes the problem really difficult. However, I think one way, at least that's one way we are trying to address the problem, to look at this problem is to structure the network. In the same way that when you program, you don't write a program with 10,000 lines with no structure. You build subroutine, and then you structure your subroutine. Essentially, we're trying to do the same kind of thing. And I do believe that one can build these subroutine within these networks, which are doing very interesting, having very interesting properties. Still, there is this beautiful question which remains. What are the functional classes which can be approximated by these machines? This is a well-posed problem on which I have no answer. But at least that's a progressively, we are trying to move progressively to, let's say, to the answer of that question. That's okay. Thanks very much.
There will be many, many questions. So, Ronnie, please.
So, if I look at the evolution, I mean, 20 years ago, what we had is an axiomatic model, and we knew how to analyze it, and we knew what it does, and then we had a regression model, dictionary, whatever, and we knew everything about it, but we could get up to 60% computation. Then came neural networks. We didn't know anything about it. Now, I'm trying to extract something from your lecture. What you're saying is that with fixing the convolutions to something that you know about the invariant property, the wavelets, it would gain me 20% more so that I could be able to interpret the networks and without going backwards in time. I mean, I'm trying to understand how to motivate students to
okay. So there's two levels of motivation. One level of motivation is indeed understand the math, how come these networks do work. But there is another level, which is the day you have a network which is like that, you know exactly what it's doing. Everything is here. Basically, the only thing that you're learning is a matrix. And if you can reproduce phase, or if you can reproduce turbulence, that means that you've captured your turbulence in this matrix of patterns, and you can analyze the object that you have. Basically, that's in that sense that now it's completely interpretable, because it's basically a union of patterns in that space.
So I have a question which is a little bit related to this. You talked about phase in the beginning, about the importance of phase. Where does phase
here? Because phase, when you apply the phase, the wavelet has a phase. When you apply this nonlinearity, because of the wavelet has a phase, it's equivalent to computing harmonics. I can look at it in the Fourier domain, but I can avoid to compute the Fourier domain, because a linear operator here is the same than a linear operator in the Fourier domain. So what I'm saying is that this thing is basically computing for me harmonics, so that when I compute a linear operator, I can build a multi-scale model. If I hadn't put these nonlinearities, if I was putting here a linear operator, it would be thing because the different scales are not correlated. So linear operator out of here because of the nonlinearity, which has created these linear dependence. And then, so that would apply here. And then there is the dictionary side. But phase is here. Phase is in the phase of the wavelets.
Some more questions? Yeah. So if you will go forward a little bit, you will see that your reconstruction images were a bit blurry.
Yeah.
Now, from the standpoint of someone who's going only deeper and not understanding this algorithm, I would say, okay, maybe use L1 loss for reconstruction instead of L2 loss. So how would you take something like that?
Basically, by putting in the final loss, we should put, in some sense, in the case of autoencoder, you can view it as almost a standard compression problem. I'm going to show the same images for the, I think it's here. You see, here you have no information. Here you reproduce a face. So somewhere you must have coded a face. There. How many bits you have? It will depend upon how big, basically, the dictionary is. If you don't have enough bits, you don't reproduce the high frequencies. You need a bigger dictionary to reproduce the fine structure of the detail. So yes, you can play a bit with the norm, and that's almost like a bit allocation. And in that case, I think we've put too much bit in the low frequency relatively to the high frequency. But at one point, you're going to be limited because your memory storage here is limited, so you cannot reproduce anything. That's all. It's an information theory condition. Yes, but there are things which are not predictable. So the question is how much you can compress phases. And at one point, if you cannot compress them anymore, you need to put more bits. So maybe you're right, we haven't compressed them well enough. The representation is not good enough to compress them. That's one possibility. But I think in that sense that these topics are not far at all from standard problem we are studying in information theory. It is, in fact, an information theory problem. We compared it with, okay, Lista doesn't work in that framework. Why? Because here in the Lista algorithm, you fix a dictionary and you impose the network to reproduce the dictionary. Here the dictionary is not fixed. Here we learn the dictionary, okay? In Lista you have two matrices, W and V, and we tried it, we did it. And when you learn the two matrices, it's not anymore learning a sparse coding. It's learning something which is not anymore the problem of sparse coding. The problem is that you have too many parameters, and if you learn all these parameters, it's not anymore solving the initial problem you wanted, which was learning a matrix which solves the sparse coding. This is why we don't use Lista or Alista. In fact, we have a paper where we compare with Alista and we show it doesn't work. You're right. There is something very similar to these models of multifractals. And we're trying, in fact, to see. The difference is that there was, in the case of fractals, you have generative. If you have a fractal, you can generate. But here, in some sense, you're solving the inverse problem. You begin with a turbulence, and you try to find a multiscale model which matches your turbulence. But in the spirit of it, I agree, and that's what we're trying to investigate, is the relation with multifractal models. We are building a model across scale which is defining in some sense, something similar to the cascade across scales that you encounter in Mandelbrot models, for example.
Okay, then we'll
Thank you.
You may approach the podium and do it in private.